Hello everyone, I'm Zhengjue Peng from Department of Earth System Science, Tsinghua University. The topic I am going to present is about cross-regional oil peltry detection using high-resolution satellite images. First, I will provide the basic knowledge about oil peltry. Oil peltries produce oil, which has wide application in the production of cooking oil, food additive, cosmetics, and so on. As the figure indicates, the production grows rapidly. Driven by the large demand, oil palm plantation expands, which causes difficulties in management and losses of biodiversity. To this end, offering an accurate and real-time assessment of poultry plantation in a large-scale region can bring significant impacts on both economic and ecological aspects. For the better monitoring and management, automatic detection of oil palm develops. Deep learning methods have shown great power, which could obtain a high accuracy. However, it requires large amount of manual annotated labels, and usually an unacceptable degradation when applying to a new different image. So, the labeling efforts needed for covering different features in different regions hinder its effectiveness from large-scale remote sensing applications using multi-temporal and multi-sensor satellite images. Domain adaptation is introduced to solve the problem. It has been developed in computer vision community. It focuses on learning a model from a source data distribution while performing on a different target data distribution. In domain adaptation, a common case is unsupervised domain adaptation, UDA, where all instances in target domain are unlabeled. Recent DA methods dive into bridging the gap in feature distribution between the source and target domains using adversarial learning and achieve encouraging results. Most of existing efforts are dedicated to image classification and semantic segmentation. However, object detection is a technically different issue because we are supposed to focus more on the object of regions instead of background or scene layouts. Existing domain adaptive object detection is still at a relatively earlier stage. DA faster RCNN employed instance-level and image-level domain classifier with consistency regularizer to reduce the domain gap. Strong-weak proposed strong local alignment and weak global alignment to improve the performance on the target domain. Existing works drive into diminishing the domain gap in both global feature level and local feature level. However, such efforts have not explored the transferability of local features, especially the different transferabilities in different regions have not been investigated and not utilized. Our study area is located in the Peninsula Malaysia, where the oil palm plantation is expanding rapidly and threatening the local environment and native species. We have two high-resolution satellite images, Image A and Image B. In this work, they are acquired from different sensors and locations, and the interval of photograph date is about 10 years. Resulting in differences in reflectance, resolution, illumination, and environmental conditions. In this part, we introduce our method in detail. We named our method as cropped. Cropped contains three losses: local transfer loss, global transfer loss, and faster RCNN loss. The local transfer loss and the global transfer loss are generated by local domain discriminator and global domain discriminator, respectively. We adopt cross-entropy loss as the local transfer loss, while we utilize focal loss as the global transfer loss. Additionally, CROPT includes context vector-based regularization like Strong-Weak. As we know, the transferable attention emphasizes on the distinction or similarity between two images. This concept is reasonable since we hope that the neural network could take more attention on more transferable regions. For example, in this study, we hope that more attention may be allocated to the oil palm plantation rather than buildings, roads, or other vegetation area. Hence, we propose local attention mechanism to reweight our network. To this end, we adopt local attention value to assess the transferability of a region. We illustrate an example region for these two transfer tags. The green points stand for the correct detected oil palms. The blue squares stand for the ground truth oil palms that are missing, and the red squares with red points stand for other types of objects like other vegetation or building corners that are detected as oil palms by mistake. We can observe that our CROPT performs better than other methods, beyond Strong-Weak by 2.21% in respect of average F1 score. To sum up, first, we propose a large-scale, real-time, and cross-regional oil palm tree detection via CROPT. To the best of our knowledge, this is the first work for domain adaptive tree crown detection using end-to-end strategy. Secondly, we implement our CROPT through constructing a local domain discriminator and global domain discriminator with adversarial learning. Additionally, we propose the local attention to highlight transferable regions and elevate negative transfer for each region. Finally, our method achieves highest detection accuracy on two large-scale high-resolution satellite images located in Peninsular Malaysia. We release our training dataset and validation dataset, hoping that our dataset can promote the development of cross-regional tree crown detection from high-resolution satellite images. This is the end of my presentation. Thank you.